Hello, today we have discussed a CFD problem solved by a square geometry which have to enclose by a virtual enclosure in Ansys workbench. As you seen that we have a square geometry which have length has 15 meter and height is 15 meter and width is 15 meter, as you seen that in clearly in figure. The virtual enclosure size which have the 30 meter in x direction, 30 meter in y direction and 50 meter in z direction. Same way in negative direction, same direction in negative direction which have x, y, z in shown in figure which have to the enclosure size. Now we come to in our theoretical part. In whole video, in whole session we have discussed to our modular laminar flow in square geometry which have to using the finite volume method, and overview of the computational fluid dynamic in CFD which have to the Ansys workbench, the importance of the understanding of fluid flow engineering in application, and objective is the step by step the modeling which laminar flow, and importance of the laminar flow in engineering application. Now which have to the some governing equation which to operate our the flow domain which have to behave in the our daily routine life to problem solving. First which the our governing equation, the governing equation for laminar flow which have to the well known equation which have to Navier-Stokes equation in 2D laminar flow. At the theoretical part which have to not in detail to how to derive, and this is the derived from the 2D direction, and these are the our continuity equation which have to which to the flow have follow it, and which have to the geometry boundary condition which have to the inlet velocity profile which magnitude which how much velocity profile we have to. Now we come to our the second part with the geometry and boundary condition. We talk about the context of the square geometry. We seen that these are square geometry which have to the inlet boundary condition which have to the widths, what type, what magnitude, the velocity flow, and slipping of is the wall slipping is the no slipping condition, and this its mean u and v velocity component is 0, and symmetry which have to the component of the gradient velocity gradient component is always to uh, 0. Now our third important part of the our CFD which have the spatial discretization, it's meant to the finite volume method which have to the a control volume which have to discuss about which these are the control volume method which to the a control volume which have to what effect of the flow behavior in whole domain to be analysis of our fluid behavior, and two with the control volume and conservation law, flux gradient which calculation in our applicant geometry, it's mean it's our square geometry which have to the gradient calculation, law of flux and conservation law which have to use in our slide. In fourth part, very important part in our finite volume method analysis which have to the our the equation discretization form, it's have to the in the there are many domain and spatial node which to be seen that in our finite volume method, and each domain which have to solve our discretization form. These are the time domain n, n1 plus 1 and n plus 2, and these are the spatial domain in when we our discretize when we discretize our governing equation to for any domain which have to the find the accuracy solution of our finite value method, which have to the each and every node to a special time zone and accuracy, we have discretized our governing equation which respect time and space. These are in vertically which have to the time n plus 1 n and n minus 1. These have to n plus 2, and these have the x plus 1 y plus 1 rj plus 1 is have to representing of our discretizing governing equation to perform the accuracy of calculation, to which have to the basic mathematics Fourier series we have to use to our discretization equation. Basically it's have two method of the temporal discretization which have to the implicit scheme and explicit scheme. The implicit scheme like domain, these are domain and which have to the primary domain which have to the include of these total domain size, and explicit scheme which to like this domain and this domain we have to converse all parameter with to saying that is had my drawing is the very poor, so I hope you understand better well what I am saying. This have the two method of the explicit two domain explicit scheme and implicit scheme. Now it our iterations to perform of this scheme we have to the use our the solution to make a algorithm which have to in generally uh, many other software we have to use to the high level coding language like Python, but in our Ansys workbench we have the predefined in solution solver in existence previously, to no need to our no need to the coding in Ansys workbench, but in other open source for source software we have to use to coding to our simple algorithm which to the updated velocity and pressure term. In this to in first node we have to assume to what the initial condition, and second node we have to take first initial value to guess value, and second updated value, and third second and first value we have to include of our the loop a certain time a certain range to the calculate our pressure turn. Same like we have to use same loop same type looping and same coding. We our velocity turn we have to assume the initial value and then the second guess value, and to solve this method we have to use to solving this method to a make a band matrix to solve the a linear system equation which have the TDMA method with to analysis the each and every node to what effect of our velocity and pressure and seen the each and everywhere. At sixth part, uh, in our result and discussion part which have the result and post processing parts, when our calculation is completed by the solution algorithm we have to visualization graphing method uh, to velocity contour and pressure distribution, what which have to velocity profile which have to gradient and contour which have to the flow domain which have to the like this. uh, as we have discussion in uh, after some time which what to effect of the velocity and effect in our Ansys workbench. At last we have to the successful of modeling laminar flow, which have to the analysis our the finite value method to what and other which have to the discussion which have the challenges, what challenges in our geometry domain, and which have the future scope in our simulation process and fluid domain, which have to contribute to it. Now it's take see our next video to detail explanation which have to the ground and effective report.